Okay, before we get started, as we start a marathon to get through this, Amanda, who is my operations and project manager, wanted me to let people know that if you didn't get stickers, they're right there on the corner. We have a People Postgres Data sticker, which is really cool. It's the mission of PostgresConf. And then we have the command prompt Mammoth, which has some story behind it. Command Prompt was actually the first company to create an integrated replication system for Postgres. It's no longer in development because obviously Postgres has replication. But all that stuff that it took them until version 10 to get, we had all the way back in 8.3. But he's a really cool little elephant or a little mammoth. So please feel free. And then if you want, my business cards are there as well. I know most people use like LinkedIn and stuff, but you're more than welcome to my cards. I might as well get rid of them. I've got thousands. Okay, let's get started. We got a ways to go. So now let's talk about kernel resource usage. This is likely not going to have too much to do, or at least the first one won't have anything to do with your Windows folks. I have no idea how to set this on Windows. But it sets the maximum number of files that can be simultaneously opened by each server subprocess. The default is 1,000 files. Very busy servers will overrun this. It's pretty easy to change. You just say, if the kernel is enforcing a safe per process limit, you do not need to worry about this setting. If you find yourself seeing too many open file failures in your logs, try reducing this setting or increasing the Linux kernel max file setting, which is in procsys fs file max. And it's live. You don't need to reboot or anything like that. You just change it. Things will be good. Shared preload libraries. This is actually a really nice feature. I don't remember when it was added, but it's been a while. It specifies one or more shared libraries to be preloaded at server start. This parameter can be only set at server start. If a specified library is not found, the server will fail to start. But it will also log, can't find this library. Some libraries need to perform certain operations that can only take place at postmaster start, such as allocating shared memory, reserving lightweight locks, or starting background workers. Those libraries must be loaded at server start through this parameter. This parameter can also help with performance of certain libraries as they are loaded on Postgres start versus called externally. Specifically, I think one of the ones that's common is PG statements. You can't use that without shared preload libraries. It's a really hefty process, and so you want to preload it so it's in RAM and it won't affect the performance nearly as much. I haven't tested this recently, but there has also been some rumors that if you use some of the external procedural languages like Python or Perl, you can preload their shared library so it doesn't have to call out to disk on every execution, which can be a performance benefit as well. Background writer. A lot of people don't mess with the background writer that much anymore. We've gotten pretty efficient with other parts of the system. I find that paying attention to it, though, is still pretty useful. This is a separate server process called the background writer, whose function is to issue writes of dirty, new or modified shared buffers. When I say writes, I'm talking about to disk. It writes shared buffers so server processes handling user queries seldom or never need to wait for a write to occur. However, the background writer does cause a net overall increase in I/O load because while a repeatedly dirtied page might otherwise be written only once per checkpoint interval, the background writer might write it several times as it is dirtied in the same interval. Meaning that as a buffer is dirtied during a time frame, it might write it more than once. Now that's okay because you're not going to allocate 50 megs a second to the background writer. You're going to allocate 5 or 10 megs a second to the background writer. Okay? And this is going to allow you to make sure that your interactive processes that are writing and causing shared buffers to be allocated are not going to pause to wait for a write and then come back. Now, under normal circumstances, you never see it anyway, right? Because it's already moving too fast. But where you will see it is if you're actually monitoring your overall performance and you're watching the trends. Your BGWriter Delay, This gets a little, for lack of a better word, hinky. I'm not sure if that can be translated appropriately. Difficult, maybe, complex. Specifies the delay between activity rounds for the background writer. This is similar to autovacuum nap time in that it's not necessarily going to do anything, but it is the rounds, it is how much it will wait to check if it does anything. In each round, the writer issues writes for some number of dirty buffers, controllable by the following parameters. It then sleeps for BGWriter delay, milliseconds, and repeats. When there are no dirty buffers in the buffer pool, though, it goes into a longer sleep regardless of BGWriter delay. The default value is 200 milliseconds. Note that on many systems, the effective resolution of sleep delays is 10 milliseconds. So setting the value, setting BGWriter delay to a value that is not a multiple of 10 might have the same results as setting it to the next higher multiple of 10. So if you set it to like 203, it's probably going to be 210 no matter what. BGWriter LRU max pages. In each round, no more than this many buffers will be written by the background writer. Setting this to 0 disables background writing. Note that checkpoints, which are managed by a separate dedicated auxiliary process, are unaffected. The default value is 100 buffers. Remember that buffers are 8K. Okay, so what we're saying here is the max number of pages the background writer will write, the max number of dirty pages will be 8K times 100. Okay, and that's kind of how you can figure out how much bandwidth or I/O this process is going to take up, because you can say, I know that every 200 milliseconds-ish, I'm going to fire to potentially write up to 100 buffers, and each buffer is 8K. So you can figure out, okay, if there's 200 milliseconds, that means there's 5 rounds per second, give or take, times 100 buffers at 8K. You can kind of determine how much I/O per second it's going to take, or potentially take. The BGWriter LRU multiplier, the number of dirty buffers written in each round is based on the number of new buffers that have been needed by the server process during recent rounds. The average recent need is multiplied by BGWriter LRU multiplier to arrive at an estimate of the number of buffers that will be needed during the next round. I know this is getting a little deep. Dirty buffers are written until there are that many clean, reusable buffers available. However, no more than BGWriter LRU max pages buffers will be written per round. Thus, a setting of 1 represents a just-in-time policy of writing exactly the number of buffers predicted to be needed. Larger values provide some cushion against spikes in demand, while smaller values intentionally leave writes to be done by the server processes. The default is 2. Don't let your writes be done by server processes. When you let your writes be done by the server processes, that's basically your connections. You are, no matter what, you're going to decrease your overall performance, because what happens is the server process must write that buffer to satisfy the D in ACID before it can move on to continue to process other queries and buffers. That's the whole point of the BGWriter. The whole point of the BGWriter is all those dirty buffers that are being created by your interactive processes, those are being written in the background instead of having the direct process trying to write and basically stuttering as it writes. Okay? So in a very simple world, you don't actually have to touch this all that often, but if you find yourself having a lot of shared buffers or dirty buffers, you're going to want to increase these values so that you're more aggressive in writing those out to the pages instead of waiting for your server processes to do so. BGWriter flush after. Whenever more than BGWriter flush after bytes have been written by the BGWriter, attempt to force the OS to issue these writes to underlying storage, essentially Fsync. Okay? Because otherwise, those buffers will come back as potentially written to disk, but they're actually still in some cache somewhere. This will say, don't let any more than 5 meg not be flushed to disk. Now, we know this works on Linux. I don't know about the other operating systems. Doing so will limit the amount of dirty data in the kernel pages cache, reducing the likelihood of stalls when an Fsync is issued at the end of a checkpoint, or when the OS writes data back in larger batches in the background. This is really important because, for example, Ubuntu, I haven't checked recently, but it used to be that by default, Ubuntu was configured that it would allow up to 20% dirty buffers of your RAM. So if you have 16 gig, it would allow for up to 4 gig before it would actually flush to disk. Now that sounds awesome if you're on a desktop. If you're dealing with data, money, that's terrible. That's a horrible, terrifying idea. So this is actually similar, it's almost a response to that. What this will do is say, most people don't hyper-tune their Linux. They don't think about it. But they hyper-tune their database, so the database will try and force those flushes. Okay? Larger batches in the background. Often that will result in greatly reduced transaction latency. That's absolutely true. But there are also some cases, especially with workloads that are bigger than shared buffers, but smaller than the OS page cache, where performance might degrade. This setting may have no effect on some platforms. The valid range is between 0, which disables forced write back, and 2 megabyte. The default is 512K on Linux, 0 elsewhere. If block size is not set to 8K, the default and maximum value scale proportionally to it. Anybody here running a block size that is different than 8K? Because you'd have to actually recompile Postgres to make that happen. Okay. Smaller values of BGWriter, and to change it is a restart. Smaller values of BGWriter LRU max pages and BGWriter LRU multiplier reduce the extra I/O load caused by the background writer, but make it more likely that a server process will have to issue writes for themselves, delaying interactive queries. Remember, this is all about performance and maintenance. This is a performance thing. If you have a process, a connection, that's what we're talking about. A user is executing queries on a connection. That is the server process. If it has to wait to do things because it's writing these blocks out, your transactions per second are going to take a nosedive. All right, PGStat BGWriter. You can monitor how the BGWriter is performing with its configuration with the PGStat BGWriter system view. If we take a look at this, we have checkpoints time, checkpoints requested, checkpoint write time, checkpoint sync time, buffers at checkpoint, buffers clean, max written clean, buffers backend Fsync, buffers allocated, and last time the stats were reset. In practice, and there are exceptions, but in practice, the most important of these values to monitor is checkpoint requested, hands down. This value represents the number of times a checkpoint has been issued either by issuing the checkpoint statement or by overrunning your max wall size. This can be a significant performance degradation, especially if you're requesting a checkpoint continuously to high transaction or bulk load. The most common mistake in Postgres performance that people make is they do not change their checkpoint timeout and they do not change their max wall size. You will see if you are under heavy write load, you can leave everything else alone. Don't touch anything. Change those two settings. Run a benchmark before and run a benchmark after, and your TPS will go like this. And then, as you saw earlier in the original first couple of pages, if you then can get your data set to sit in shared buffers, you're good to go. Okay. Asynchronous behavior, effective I/O concurrency. Sets the number of concurrent disk I/O operations that Postgres expects can be executed simultaneously. Remember when we were talking about SSDs and concurrency? This is what we're talking about. Raising this value will increase the number of I/O operations that any individual Postgres session attempts to initiate in parallel. The allowed range is 1 to 1,000 or 0 to disable. Currently, this setting only affects bitmap heap scans. I do not know if that's still true. It may have changed. We're a couple of releases back. For magnetic drives, a good starting point to this setting is the number of separate drives comprising a RAID 0 stripe or RAID 1 mirror being used for the database. So what they're basically saying is that if you have 4 drives, 4 spinning disks, set it to 4. Okay, because really a single drive can really only kind of do, unless you've got ordered writes from a RAID controller, 1 write per spin. Right? So you don't really have concurrency. The concurrency is created by the stripe in the RAID controller. For RAID 5, we're not going to talk about that because no one in their right mind runs a database on RAID 5. Anybody here running RAID 5? Thank you. Please don't do that. Really? Don't do that. RAID 5 is terrible for databases. Great for file systems. Terrible for databases. However, if the database is often busy with multiple queries issued in concurrent sessions, lower values may be sufficient to keep the disk array busy. A value higher than needed to keep the disks busy will only result in extra CPU overhead. SSDs and other memory-based storage can often process many concurrent requests, so the best value might be in the hundreds, and that is true. I've done some testing, and we'll actually get down to this graph here in a second. Actually, let me finish this, then we'll get there. Asynchronous I/O depends on effective POSIX fadvise function, which some operating systems lack. If the function is not present, then setting this parameter to anything but 0 will result in an error. On some operating systems, Solaris, the function is present but does not actually do anything. Anybody here running Solaris? Yeah? Not Oracle, but Solaris. Okay. So, Solaris is not a bad operating system. It's a shame that evil won't let it go and just let it be truly open source, or at least GPL compatible. The default is 1 on supported systems, otherwise 0. This value can be overridden for tables in a particular table space by setting the table space parameter of the same name. Table spaces are cool. If you don't know what they are, think of directories. It basically allows you to say, these tables, these relations, are over on these disks. And these tables and these relations are over on these disks. So being able to change that works really well, because think of a partition data set. Let's say you got 5 years of data and it's 50 terabytes. Well, in reality, you're probably only querying the first 6 months to a year of that data. So move the 4 years of data over to some big SATA array, and move the 1 year to 6 months worth of data over to the SSD array. You can change the effective I/O concurrency on the SSD array to be more appropriate and leave the larger, older data set alone. Testing with the TPC style benchmark shows that on local systems, setting this between 0 and 48 keeps the TPS within noise level. However, testing also shows that on cloud systems such as Google Cloud Compute, setting this to anything greater than 0 results in approximately 10% performance degradation on TPS. I have tested this more than once. I don't know if it's currently true, but back when I wrote this, I was stunned, because if you look, GCE, my TPS was significantly higher with no effective I/O concurrency, versus a local disk where it was all within really noise levels. Now, the question with the local disk, and I didn't test this on my local disk, is if I would have set it to something like 200 or 250, because it was an SSD, would I have seen the benefit? Other people have reported that if you are running SSDs locally in an array, that yes, you will see a benefit by increasing this up to like 200. But I have not observed it. And I certainly have not observed it on network-based file systems like GCE or, say, Amazon with EBS or something like that. Max worker processes sets the maximum number of background processes that the system can support. This parameter can only be set at server start. The default is 8. When running a standby server, you must set this parameter to the same or higher value than on the master server. Otherwise, queries will not be allowed in the standby server. Max worker process, the reason you need this is because it has to do with anything that is background oriented, including like your parallel workers. So if you're using parallel query, which is actually quite mature in 10 and 11, it's not real mature in 9.6. If you don't have enough max worker processes, other things won't work. You'll just run out of resources. Max parallel workers per gather sets the maximum number of workers that can be started by a single gather node. Parallel workers are taken from the pool of processes established by max worker processes, which was the previous one we just talked about. Note that the requested number of workers may not actually be available at runtime. If this occurs, the plan will run with fewer workers than expected, which may be inefficient. Setting this value to 0, which is the default, disables parallel query execution. I don't recommend 0 on 10 or 11. On 9.6, it still may make sense because parallel query is relatively limited in 9.6, but it is not in 10 and especially not in 11. You need to be careful though, because the problem with parallel query is that by default, Postgres basically goes and says, here's my query, here's all my joins, all my sorts, and all that. And it goes, I've got this one, I've got this one, I've got this one, I've got this one, I've got this one. Merge it all together and deliver it. Okay? It's a very deterministic way to figure out how much performance you're going to get out of something. The problem is that with parallel query, the downside is that it might go, if you think of a hand, all fingers go out on its own, collect each of the joins independently, and then come back, merge them in all together, and deliver it to you. Now that's highly efficient and it's highly effective if you have the resources. If you don't have the resources, you can actually have less performance and reduce, or I should say increase the load of your server because you're doing too many things at once. Because we don't have the ability to say, only do it if load is less than 2, or only do it if we only have less than 20 connections, or only do it if only 50% of work mem is used. We don't have the ability to do that. So you do need to pay attention to this, especially in the newer versions. It's not bad, don't get me wrong, it's a beautiful feature, and it makes Postgres scale far beyond previous versions, but the cost is you got to pay attention to it. You got to be able to manage it. Old snapshot threshold sets the minimum time that a snapshot can be used without risk of snapshot too old error occurring when using the snapshot. This feature correlates to the transaction isolation levels of serialization and repeatable read. If you have an open snapshot, a transaction, and that transaction is using the isolation level of serializable or repeatable read, and the life of that snapshot exceeds this value, you may throw an error which will cause the transaction to roll back. Beyond the threshold, old data may be vacuumed away. This can help prevent bloat in the face of snapshots which remain in use for a long time. To prevent incorrect results due to cleanup data which would otherwise be visible to the snapshot. What they're talking about here is that they're talking about long-running transactions within a particular isolation level. And if you think about serializable, the most common thing of serializable would be, say, think of the shopping cart methodology, where you have an open transaction where someone has taken and said, I want to buy X. Well, how many of us have logged into a website and said, I want to buy X, realize they've had too much vodka, and they put the phone down? Well, that transaction is still, well, I've done it. Okay. There are times when I'll get a package from Amazon, and I don't remember why. And I actually bought I don't know if you guys will know what this is, but a hammock tent. It's basically a tent, which is a hammock. It doesn't sit on the ground. You hang it like a hammock between two trees. This is a few years back, and it was one night, and I wasn't drinking too much. Well, some would argue with that. I think I wasn't drinking too much. And 2 days later, I had a tent, and I had no idea where it came from. I had to actually log into Amazon. I'm like, either I've been hacked or I need to put the bottle away. But that's what this is about. So someone says, I want one of these, and then they leave or they shop for a long time or something like that. The problem is that you're allocating that number, right? You're saying, okay, I actually only have X minus 1 left. Well, you don't want to leave it like that unless the person eventually checks out. So old Snapshot Threshold says, after so much, I'm just going to roll that transaction back so that people can continue to go forward. And we won't have bloat and things like that. Hammock tents are really nice, by the way. The only time I've ever been backpacking where my back wasn't sore. Okay, back-end flush after. Whenever more than back-end flush after bytes have been written by a single back-end, attempt to force the OS to issue these writes to underlying storage. This setting does not affect writes by the background writer. This is actually just like the background writer, but for server processes. So you don't end up in a situation where a server process has written many megabytes of data and it hasn't been flushed to storage. So now we're going to say, if we reach X, we're going to flush it to storage no matter what. The goal would be to never hit this. The goal would be that your background writer is configured to make sure that you never even care about this parameter. Write-ahead log. It is all about the D in ACID, durability. Wall level. Sets the wall level. Options are minimal, replica, and logical. The default is minimal. If you want to use streaming replication or point-in-time recovery, a minimum of replica is required. Just use logical. The rest of them just don't matter. And the reason I say that is, yes, if you're using logical, you are going to issue more writes. You are going to use more I/O, but you don't want to have to restart Postgres when you realize you should have just listened to me in the first place. And the reason is logical gives you logical replication. Logical gives you the ability to connect to Postgres and stream to Kafka. Logical gives you the ability to connect to Postgres, and I don't know why anyone in the world would do this, but stream to Mongo or MySQL. It's logical that gives you all of those really cool, why in the world am I doing this? But it's cool, so I'm going to features. So just leave it at logical. You also need it for logical replication. It is a restart to change. Fsync. This is very simple. The default is on. Your default is on. Do not under any circumstances turn this off. You will corrupt your database. It shouldn't even be a parameter you can change, period. Don't touch it. I don't care if it's pretty. Don't pet it. Don't modify it. Don't remove it. Leave it alone. I guarantee you, if you turn this off, you're going to end up in an environment where you are either A, fired, B, up for 3 days, or C, fired. Don't touch it. Leave it on. Yes, it's a performance hit. Make it up somewhere else. I don't care if you're bulk loading. I don't care if you say, hey, this gives me 20% performance improvement. It won't, but if it does, something else is wrong. Don't touch it. Okay? Can I be any more clear? Good. I know why. So to explain why, what Fsync does is it sets so that every time you're writing to the disk, it issues a file sync from the kernel call to make sure that that data is actually on the disk. Without this setting, you are essentially being lied to continually about whether or not your data is on disk. And let's say some guy who's drinking coffee walks into your data center and goes, oops, and the server crashes. Well, no big deal. You reboot, clean it up, whatever. If you have Fsync, everything comes back up. Sure, you might lose the last committed transaction or something through the transaction log, but your data is going to be consistent. You're not going to have foreign key violations. Any query you run is going to come back correctly. If Fsync is off, you have Chinese in a Russian database. Okay, it doesn't work. Okay? Synchronous commit. This is a tricky one. Specifies whether transaction commit will wait for wall records to be written to disk before the command returns a success indication to the client. Valid values are on, remote apply, remote write, local, and off. This also has to do with synchronous replication, which is why you have the weird like remote apply. The default and safe setting is on. When off, there can be a delay between when a success is reported to the client and when the transaction is really guaranteed to be safe against server crash, e.g. written, actually Fsynced written to disk. The maximum delay is 3 times wall writer delay. When not used with synchronous replication, this is purely a performance setting. Some people disagree with me on this. I will explain why. In general, you should see about a 10% increase in write performance without synchronous commit. Notice this table here with 16 connections, and imagine if we have 64. If it's on, I get 817 TPS. If it's off. If it's on, I get 724. That's over 10%. Now, what is the actual argument here? First off, is there anybody here not running an asynchronous app? 95% of apps are now what? Web-based, something like that. The web by its very nature is asynchronous. You hit post, hits the web server, hits the middleware, connects to the database, writes a query. You got all this stuff going on before you ever even get to the database. Now, what's more likely to happen? Nginx or Apache or Tomcat dies? Or someone decides to disconnect in the middle of their session by killing Chrome? Or that Postgres died? That's what we're talking about here. If you have synchronous commit on, what it says is I must go through every single layer till I get to that connection. I have authorized, I have sent my password, I have executed a query. That query must then hit the wall, your write-ahead log. The wall must write it to disk and then return back and say, I have successfully written these bytes to disk. Okay? The difference when it's off is it gets all the way down, you execute the query, and Postgres says, I got this. You don't have to go through all that wall crap. Now, people say, well, why would you do that? There's a risk. You're trusting Postgres with your data. Why not trust Postgres with your data? You do get some people that are relatively pedantic. It's okay. They're like, no, I must absolutely wait till it's written on disk. Well, that's fine, but I want to go faster, and I trust Postgres with my data. Otherwise, I wouldn't be running it. It's why I don't run MongoDB. I want a database I can trust. Okay? Anybody here running MongoDB? Yeah. He's like, okay, so quick moment. MongoDB is great, kind of. Not really. I'm just trying to be nice. So if you use Mongo for what Mongo was originally designed for, Mongo's actually pretty cool. You want to have some JSON data as an edge server that is basically a cache, right? You're not relying on Mongo to save your bank information or to process financial transactions or healthcare information, anything important. Use it to store metadata. It's great at that. It's really good at that, honestly. But when you use Mongo because you have a bunch of web developers that think JSON is like the stuff, it's like the chocolate ice cream when you should be having vanilla, that doesn't work. Use a real database for that, which is Postgres. I don't know of any other real databases. They tell me they're out there. I haven't seen one yet. Okay, I might be biased. Replication and synchronous commit. This is a big old paragraph, but it is relevant because we're talking about performance. If synchronous standby names is non-empty, this meaning you have synchronous standbys, this parameter also controls whether or not transaction commits will wait for their wall records to be replicated to the standby server. What does this mean? I'm not going to go through this whole paragraph. I'm going to boil it down. What this basically means is don't run synchronous replication. Okay? That's what it actually boils down to. The problem with synchronous replication is it's slow. Very, very slow, and you are guaranteed at some point an outage. And this is why. Synchronous replication in Postgres is correctly designed by engineers, incorrectly designed for people who have production servers. And this is why. Okay? What it says is, on my master, on my primary, I have these writes that have come across. I've accepted these writes, but I cannot commit these writes to disk until I go over the network to this other database server, and this other database server puts it in the wall, writes it to disk, and then goes all the way back over the network and says, yo, I got this. And then the primary says, cool, writes it to disk and lets you continue on. Now that is absolutely 100% awesome if we're in an environment where under no circumstances can we lose data, right? There's no arguing that. Like I said, correctly designed by engineers. Problem is, I was told that car analogies won't work, but as we know, engineers sometimes design things that are only correct until you use them. Okay? Here's your problem. If that secondary goes down, your master stops working. Why? Because you're synchronously replicating. Your master, your primary, is waiting for the secondary to say, I got these writes, you can continue. Synchronous replication, beautiful for keeping data safe, horrible for performance and uptime. Okay? The other part of this is I've run, like I said, I worked on thousands of machines. And the lag time, as long as you have the right network interconnect, for asynchronous replication is almost non-existent. I say almost because it does depend on your load, but I'd rather get 1,000 TPS versus 500 TPS as a general rule. And you're basically doubling your write load and adding a network stack if you're using synchronous replication. Okay? In newer versions, there are some niceties, like we have quorum commit, which means that you can be running synchronous replication, and as long as a certain number of synchronous servers respond that they have the data, it will continue forward. That's actually how Amazon Aurora works. If you've heard of Aurora, Amazon Postgres Aurora, what it does is when it writes everything out, one of the reasons it's so fast is it writes out to multiple volumes, and it uses quorum commit to determine when it's allowed to move forward. So it's a nice feature. All right, wall sync method. The operating system call that would be execute to force writes to disk. On Linux, the default is fdatasync. I've never seen anything but fdatasync be faster on Linux. On Windows, I think it's OpenSync that they recommend. Full page writes. When this parameter is on, the PostgreSQL server writes the entire content of each disk page to wall during the first modification of that page after checkpoint. Do not turn this off. It can lead to corruption. That is just the simple truth. Now, this does not apply to proprietary versions of Postgres from Microsoft or Amazon. Aurora specifically, it does apply to RDS. But Aurora and the Azure Postgres both have their own back-end storage that's different, and they do not require full page writes. Wall compression. When this parameter is on, the PostgreSQL server compresses a full page image written to wall. When full page writes is on or during a base backup. A compressed page image will be decompressed during wall replay. The default value is off. Only super users can change this setting. Turning this parameter on can reduce wall volume without increasing the risk of unrecoverable data corruption, but at the cost of some extra CPU spent on compression during wall logging and on the decompression during wall replay. Here's the thing. It only compresses full pages. Pages are 8K. Those compress very fast. CPUs are very fast. Go ahead and turn it on. Try it out. See how it works for you. You're not risking anything really because your CPUs are already fast and it can actually increase performance. Wall log hints. When this parameter is on, the PostgreSQL server writes the entire content of each disk page to wall during the first modification of that page after a checkpoint, even for non-critical modifications of so-called hint bits. If data checksums are enabled, hint bits updates are always wall logged and this setting is ignored. You can use this setting to test how much extra wall logging would occur if your database had data checksums enabled. This parameter can only be set at server start. So by default, Postgres does not checksum its writes. Postgres has a long history of saying, we're a database, not a hardware RAID controller, not an OS file system manager. Right? So it didn't used to checksum stuff. But what we found over the years is you can't trust RAID controllers. You can't trust Linux to necessarily write things. Now, it's rare. Don't get me wrong. It is very rare. I think in 20 years, I've run into a checksum problem maybe half a dozen times in 20 years. But depending on what you're storing in your database, just once could destroy your whole company. So check it out. Checksums are a definite performance hit, however. There is no way around it. There is no, oh, if I do this, it won't be a performance hit. No, you turn it on, it's a performance hit. Period, the end. Wall buffers. The amount of shared memory used for wall data that has not yet been written to disk. The default setting of -1 selects a size equal to 1/32, about 3%, of shared buffers, but not less than 64K, nor more than the size of one wall segment, which is typically 16 meg. This value can be set manually if the automatic choice is too large or too small, but any positive value less than 32K will be treated as 32K. The contents of the wall buffers are written out to disk at every transaction commit. So extremely large values are unlikely to provide any significant benefit. However, setting this value to at least a few megabytes can improve write performance on a busy server where many clients are committing at once. The auto-tuning selected by default setting of -1 should give reasonable results in most cases. That is true. I have yet to see a situation where I cared enough to change it, at least when testing. Leave it to -1, let it do what it needs to do. It's pretty smart that way. Wall writer delay. This is similar to the background writer, but now instead of talking about dirty pages, we are talking about the wall of the write-ahead log. Specifies how often the wall writer flushes wall. After flushing wall, it sleeps for wall writer delay milliseconds, unless woken up by an asynchronously committing transaction. If the last flushed happened less than wall writer delay milliseconds ago, and less than wall writer flush after bytes of wall have been produced since, then wall is only written to the operating system, the kernel cache, not flushed to disk. The default is 200 milliseconds. This feature does open a very small risk of data loss, but not corruption for uncommitted data. This is very similar to synchronous commit. You are trusting that you have reliable hardware, that you have a reliable software or operating system, and that you have a reliable database. If you're running anywhere near reasonable hardware on Linux LTS and Postgres, that is what you have. So make sure that you make use of this because it will be a performance benefit. Now, it's true. If you have uncommitted data, keep that in mind, what I just said, uncommitted data. The data that doesn't technically exist yet. You have not violated the D in ACID. And you crash, you may lose that data. But it's not going to change your consistency. It's not going to break foreign keys. It's not going to corrupt anything. It's like the transaction never happened. That's no different than the fact that you're running a web app and you hit X on Chrome in the middle of a process. Okay? Wall writer flush after. specifies how often WAL-writer flushes WAL. If the last flush happened less than WAL-writer delay milliseconds ago and less than WAL-writer flush after bytes of WAL have been produced since, then WAL is only written to the operating system, not flushed to disk. If WAL-writer flush after is set to 0, then WAL data is flushed immediately. The default is 1 megabyte. Very similar to the back-end process flush afters. It's basically a cache within a cache, just so you're not writing unnecessary data, because we're only talking about a very small amount of data, right? These two are actually one of my favorite settings. Commit delay. Commit delay adds a time delay measured in microseconds before a WAL flush is initiated. This can improve group commit throughput by allowing a larger number of transactions to commit via a single WAL flush. If the system load is high enough that additional transactions become ready to commit within the given interval, however, it is, within the given interval. However, it also increases latency by up to commit delay microseconds for each WAL flush. Because the delay is just wasted if no other transactions become ready to commit, a delay is only performed if at least commit siblings, other transactions, are active when a flush is about to be initiated. Also, no delays are performed if Fsync is disabled, which you will never do because Fsync is not to be touched and will be left on. The default commit delay is 0, no delay. Only super users can change this setting. Beginning in 9.3, the first process that becomes ready to flush waits for the configured interval, while subsequent processes wait only until the leader completes the flush operation. While it may appear to be redundant with WAL-writer delay, the WAL-writer actions take place after a commit. The commit delay is used before the commit to potentially group together or group commit siblings together, and thus you see commit siblings. The short version of this is if you have a lot of highly concurrent small transactions that are being committed, basically you have a busy server, Postgres will say, hey, I've got these 5. Let's do these 5 at once. Instead of 1, 2, 3, 4, 5, we got a bucket and we write it out. So if you configure it correctly and you can test it, benchmark it, you can actually see quite a bit of benefit. Checkpoints. Checkpoints now are something that I don't even really think we need to have. They made sense in the older versions, but now with BGWriter and with the WAL log and everything else you can do, it's almost kind of a legacy thing, but it is still something you definitely want to configure. A checkpoint is a point in the transaction log sequence at which all data files have been updated to reflect the information in the log. All data files would be flushed to disk. Basically, it's a consistency check. Everything, all the different changes, everything that's sitting around, it goes snapshot, okay? The checkpoint command forces an immediate checkpoint when the command is issued without waiting for a regular checkpoint scheduled by the system. Checkpoint is not intended for use during normal operation, meaning just during your normal day, don't issue a checkpoint. You do need it when you're about to do a backup, like a base backup for replication, checkpoints are issued, things like that. But during normal operation, it's not needed. The default checkpoint settings are almost always too conservative. I would say they are always too conservative, not almost. Using the same test but with 16 terminals connections as before, consider the below. My checkpoint, the default, 5 minutes. Max wall size, 1 gig. TPS, 740 transactions per second. Okay? All I do is change it to 10 minutes, increase max wall size to 2 gig, and I've got over a 10% improvement. Personally, I would set that to a minimum of 1 hour and have your max wall size be somewhere around 5 gig. Because you really only need this checkpoint, A, because it makes you feel better, and that's valid, don't get me wrong, and B, when you're running base backups. binary full backups. And that'll do it by itself. Checkpoint timeout. The amount of time to wait before a checkpoint is issued, the default is 5 minutes and almost certainly too low. The maximum is 1 day. Checkpoint is used to ensure that all data has been written to disk. That's true, except that we already have 17 other parameters that are making sure that all my data is written to disk. Not to mention I have the wall log, which I can recover from just in case some of my data hasn't been written to the page files. So my recommendation is at least 1 hour, possibly more. Max wall size. Maximum size of wall files, PGXlog, that's now in the newer versions, it's PG_wall, W-A-L, that are allowed before a checkpoint is issued by Postgres. This is a soft limit. Wall size can exceed max wall size under special circumstances, like under heavy load, a failing archive command, or a high wall keep segment setting. If you are running a modern version of Linux, specifically 9.6 or above, do not use wall keep segments. Use replication slots. That's what they're for. Okay? The default is 1 gig. Increasing this parameter can increase the amount of time needed for crash recovery. Wall keep segments is now a deprecated parameter, only supported for backwards compatibility. That's true. Now you use max wall size or replication slots. Min wall size. As long as wall disk usage stays below this setting, old wall files are always recycled for future use at a checkpoint rather than removed. This can be used to ensure that enough wall space is reserved to handle spikes in wall usage. For example, we're running large batch jobs or bulk loading. The default is 80 megabyte. Okay, checkpoint completion target. This is another one of my pet peeves. Okay, the point of checkpoint completion target is to smooth checkpoints. Because if you think about it, if you're under heavy load and all of a sudden you issue a checkpoint and the entire system wants to go on disk, okay, that can be very, very expensive based on how much data you have running. The problem is, this specifies the target of checkpoint completion as a fraction of total time between checkpoints. The default is 0.5. To determine, here's the key, to determine how often a checkpoint will occur with this setting, use the following formula. Checkpoint timeout divided by checkpoint completion target. Think about that for a second. What is the default checkpoint timeout? 5 minutes. We already know that's going to kill your performance, period. But now we have this other parameter that says actually checkpoint timeout is not 5 minutes, it's 2.5. So by default, Postgres will checkpoint every 2.5 minutes. Right? Set it to 0.9, increase your checkpoint timeout as much as it makes you feel comfortable, walk away, have a cup of coffee, and laugh as everybody else is moving slow, and you are not. Checkpoint flush after. Whenever more than checkpoint flush after bytes have been written while performing a checkpoint, attempt to force the OS to issue these writes to underlying storage. We've already talked about all these flush after settings. Doing so will limit the amount of dirty data in the kernel page's cache, reducing the likelihood of stalls when an Fsync is issued at the end of a checkpoint. This is a very real thing. There are times when you are pushing so much data that your kernel cache just gets overloaded. And Linux is trying to push out all the data. And you will see spikes in your, if you're running something like sysstat with IO stat, you will see spikes where your IO just jumps. You have no idea why. It doesn't make sense. And there's a good chance it's because your kernel cache is getting overrun and there's not enough data being written out to keep it full or empty enough. Checkpoint warning. This is one of my favorite settings because it makes no sense as to why it's set the way it is. If you are checkpointing more than this value, Postgres will warn in the log. The default is 30 seconds, and it is too low. So I want you to think about something. It's going to tell me, yo, DBA, you're checkpointing more than every 30 seconds. Well, shouldn't it actually tell me anytime I checkpoint more than checkpoint timeout divided by checkpoint completion target? Why are you telling me at 30 seconds? At 30 seconds, I'm already screwed. My alarms are going off everywhere. On-call people are being paged. My boss is yelling at me. The website's stalled, right? Your world is ended at this point, right? You're crawling under your desk looking for a manhole cover to escape. So set this to at least the calculation of checkpoint timeout divided by checkpoint completion target. Because it's going to tell you, hey, your checkpoint timeout and checkpoint completion target are wrong versus an arbitrary, oh, by the way, every 30 seconds you're checkpointing. Okay, planner method configuration. The following parameters are useful for determining why certain query plans are choosing different paths. They should not normally be turned off in the configuration file. Instead, use set to test your query. For example, set enable bitmap scan to off, explain, analyze verbose cost query. So where this is really useful, I find, I mean, they're all useful, but the ones that are really useful are things like enable index scan, enable index only scan, enable nested loop. Because what you can do is you can run a query, and you're like, this doesn't make sense. It's so slow. I got everything indexed right. What's wrong? Okay? So for example, set enable seek scan to off. You're forcing an index scan, and yet the planner still doesn't use the index. Why? The index is probably bloated out too far in that the planner says, I don't care what you say, it's better to use seek scan, or your index is corrupted and you don't know it. That type of thing. If you're an SQL developer and you really get into this stuff and you're looking for micro optimizations, it's also useful. Every once in a while you'll run into a query where depending on where you have a particular clause in the query, it will choose a different plan. Now, that doesn't happen so much anymore. Our query planner's actually gotten pretty good. But every once in a while it still does, and what you can do is, for example, if you're getting a merge join and you shouldn't be, or you're pretty sure you shouldn't be, you can turn that off and see if the new plan, which doesn't use a merge join, is faster. And then you can start diagnosing where, who, what, when, where, why it's doing what it's doing. Okay. Planner cost constants. Planner cost constants are largely arbitrary and used to determine a value of retrieving or operating on a tuple, a row, based on the type of access the planner has chosen, index, sequential, blah, blah, blah. You can set these options in the PostgreSQL.conf, but you may also test them in a similar fashion to planner method configuration by using set within the session. A really good, so for example, seek page cost. This is the cost of sequentially fetching rows from the disk. Generally speaking, the default is fine. It's absolutely true. And the reason this is weird is because these are arbitrary. So if you set them all to the, like if you were to take them all and multiply them by 4, every single one of them you multiply them by 4, you're going to get the same thing as what you had before because they're all interrelated. So seek page cost is set to 1. Random page cost, the cost of a random fetch across or access to the tuple from the disk. The default is 4, meaning that the planner will prefer sequential scans in many queries, if not most queries. If you are running RAID 10 or SSDs, you can usually set this to 1. Realistically, if you're running anything of any moderate I/O performance, make random page cost and seek page cost the same. I don't care if it's 4, 4, 1, 1, 2, 2, it doesn't matter. Make them the same. Because then the planner is going to choose based on equality which one makes more sense, And especially when you're dealing with, say, 20,000 IOPS EBS volumes or SSDs, it really doesn't matter if it's a seek scan or a random fetch. Okay? And by setting it to the same, it is going to allow you, the planner to say, yeah, we're not worried about an index scan. Now you think to yourself, well, of course I want an index scan. Well, no, you may not. And here's where. Let's say you have 1,000 rows. It may actually be faster just to scan all 1,000 rows than to go all the way to the index, transverse the tree of a B tree, find all your leaf pointers, and then go back to the heap to find what rows to return. Now the question is, how much faster? That depends. But I have actually seen situations where you're literally talking about a 20 millisecond query versus a 22 millisecond query. At which point, why do you care? Okay. CPU tuple cost sets the planner estimate of the cost of processing each row during a query. The reason you need all of these is because CPUs used to be slow. They're not anymore. So it's actually not expensive, generally speaking, for a CPU to process a tuple. I would leave this one alone. Index tuple cost sets the planner estimate of cost of processing each index entry during an index scan. Operator cost, greater than, less than, greater equal than, that kind of thing, sets the planner estimate of the cost of processing each operator or function executed during a query. Parallel setup cost sets the planner's estimate of the cost of launching parallel worker processes. Keep in mind that a lot of the worker processes are pre-launched, so it can actually be a very low value. Sets the planner's estimate of the cost of parallel tuple cost. Sets the planner's estimate of the cost of transferring one tuple from parallel worker process to another process. When does that happen? It's when one process gets the data it needs to be able to hand to another process for merging or whatever to deliver to the client. Min parallel relation size sets the minimum size of relations to be considered for parallel scan. I don't remember what the default is. All of these are literally, you got to test them. There's no good parameter. It's not like shared buffers where I can say to you, here's a general grouping of ideas of how to correctly set shared buffers. These are different than that. What I can tell you is, like I said, if you've got any reasonable I/O, the first two, seek page and random page, make them the same. I have found that CPU tuple and CPU index cost on newer boxes is fine, just leave it alone. Operator cost, however, can be changed. Sometimes it needs to be increased based on how intensive your operator usage is. Right? If you're processing lots and lots and lots and lots of queries over greater than, less than, or any other operator, that can increase the cost to the planner, and it might make more sense for the planner to be a little more aggressive or less aggressive depending on what you're doing. Short of it is, you got to test. Everybody loves testing. Unit tests are great. All right. Effective cache size. This is one of the misunderstood settings. Effective cache size is not a memory allocation. If you set this to 16 gig, it is not 16 gig of data being set aside for some cache. Okay? What this is a hint to the planner to determine how much data may be in active cache. Remember that PG buffer cache query? Active cache. The calculation of effective cache size is percentage of cached plus shared buffers equals effective cache size, where percentage depends on the workload, but usually the higher the better. If set too high, it can be a performance hit, as the system will prefer index scans over sequential scans. But again, remember what we're dealing with here. All of these recommendations, everything you read in these docs, are all based on the idea that we are all running 4 7200 or 10K SAS drives in a RAID 10 with a small battery-backed cache. Generally speaking, nobody's doing that anymore. They're either on a cloud, in which case you don't even have to worry about it because they've got all kinds of weird stuff going on, or you're on-prem and you've got SSDs. Again, not really a difference in cost. So the goal here is not to worry so much about whether or not you're going to hit an index scan, but to make sure you actually will hit the index scan. That's what effective cache size effectively does, is it says, I know that this data is cached, and therefore not sequential scanning is going to be faster. And remember, it is not a memory allocation. Okay. Genetic query optimizer. Absolutely, what I'm about to say is absolutely true. Discussion of this feature is outside the scope of this training. Generally speaking, the defaults work best. I'm saying two things here. One, I have no idea what this thing does. I've never understood it. I don't want to understand it. I know it works. I'm happy it works. Okay, it's kind of like my microwave, right? I know when I push it 1 minute, 30 seconds, my coffee will be reheated and I'm good to go. I don't care how it did it. That is what this is with Postgres. If you want to look into it, if you're one of these people that really likes to stretch their brain in ways that it's already a solved problem, but maybe it's not a solved problem, so I'm going to stretch my brain to make it a not solved problem that's already solved, go for it. Dig into the code. Awesome. But that's what it is. The one thing, I can't remember what the setting is, but there is a setting in here that it has to do with the number of joins. And if you look under the heading Genetic Query Optimizer, it says something like min joins for activity or something, and it says basically if you have more than 12 joins, that's when this guy will kick in. So if you are averaging large queries, where not 12 joins is a lot of joins. If you're doing 20, 30, 40 joins, you might want to look into that. But this is not something that, honestly, it's just not my scope. All right, other planner options. This is actually really important. Default statistics target. This is the amount of statistics to... Okay. So I got a story. I did a presentation at the University of Northern Arizona. That would be in Arizona. That's in the United States. It's an interesting state, very dry. It has this small thing called the Grand Canyon in it. And I was at the ACM. I don't know if you guys know what the ACM is, but in the States, that's kind of our computer science club. And it's applied, I don't even remember what it stands for anymore because nobody joins it. But it's an old school computer science club, basically. Most of the universities have it. And I was on a stage very similar to this where I had two screens. They were larger, but there were two screens. And I was talking to a bunch of students. All of them were about sophomores, so say year 2 in college. And I was talking about open source in general. What is open source? Why is it good? Because, of course, this was back in the day when Sun Microsystems and Microsoft, the two of them owned universities, right? They didn't teach you how to do computer science. They teach you how to do Java or .NET. Now, it's not that that's bad because they are producing people that can generate work, which is good. But they don't necessarily generate people that can think, and that's bad. So I'm having this long training going on about open source, all the cool things about open source, all the things you can do, what Perl is, what Python is, what Postgres is, what Java, everything. And there's this kid sitting right about where this guy is sitting right here. I'm going to point at you, sorry. And his phone rings. And I'm bringing this up because this is not the first time a phone has rang in this training. And I don't mind, sometimes people's phones ring, you forget to turn it off. That's not a big deal. This kid answered the phone, and he didn't answer the phone like, hey, I'm busy, I gotta get back to you. He full on was like, yo, what's going on, man? Now, I don't know if you noticed, but I don't mind pointing people out. And I stopped, and I'm like, really? Really, right now, you're going to do this right now, and everyone's looking at him. And he's like getting offended. He's like, how dare you interrupt my call? And in the same situation, I'm like, you realize we're being recorded right here, right? You realize in front of all your peers and your professors who are in the back of this room, you are answering the phone while someone is giving a presentation. Don't do that. It's rude. Anyway, so the amount of statistics to be stored by analyzed for use by the query planner. It is an arbitrary value used to determine the volume, the size, the number, of statistics collected on a relation. And really, it's not even the relation. It can be also on a column, not the relation as a whole. The larger the value, the longer analyze takes, but generally the better the plan. The value can be set per column on a relation to store a higher amount of statistics on a selective basis. The simplest way to know if you need to increase the value is to review and explain analyze plan. If we look here, look in the bold. This might be kind of hard to see, but the last line of this plan here, it says, here's my estimated rows, 52, and here's my actual rows, 3,600. That right there is telling you, under no uncertain terms, your default statistic target is too low, period. And you're going to get bad plans. Bad plans mean bad performance, okay? The parameter can be tested per session. For example, set default statistics target to 200, analyze the relation, explain analyze for bloats, blah, 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 and then you'll see the row estimates line up. Now, this is not a big deal on most databases, but there are databases where you're analyzing so much data that the statistics are just, you're going to end up with a huge amount of data in PG statistic. So what you can do instead is on, I would say on select, don't do it across the board, but on select relations where you know you are querying all the time a particular where clause, where x equals whatever. You can increase the statistics on x, on that column only, and then run analyze. So you don't have to bulk out your PG statistic table with a bunch of unnecessary statistics. As a general rule, don't do that. I wouldn't recommend it as a general rule, but there are definitely times when you're talking about, especially larger data sets, where you might want to do that with just one column within a particular table. Constraint exclusion, a setting of on, off, or partition. The default is partition and the recommended setting. The use of constraint exclusion allows a planner, via check constraints as well as planning, to determine which relations within a partitioned set contain the data the query is looking for. Now, what does that mean? It means that you can set up a partition set, let's say over 100 partitions, and you can say this partition, based on this check constraint, only has this data. And that way, when you query the partition set, the planner will only look in the partition that matches the check constraints for that data, instead of traversing the entire partition set. That being said, nowadays the planner is good enough to where you usually don't need the check constraint because the planner knows already. So then the check constraint becomes a situation where you are restraining the data because you want to make sure only that data is in that partition, versus necessarily needing the planner to figure that out. I'm not sure how it applies with the newest versions of partition. In fact, I do. In version 10 and 11 of partitioning, now that we have actual partitioning, this is probably a legacy setting. From collapse limit, the planner will merge subqueries into upper queries if the resulting from list would have no more than this many items. Smaller values reduce planning time but might yield inferior query plans. The default is 8. This is that setting with the genetic query optimizer thing we were talking about. Setting this value to GQ threshold or more may trigger the use of GQ planner, resulting in non-optimal plans. All right. Is it 1:30 that we break out of here? Okay, so we're not going to get through this. We're not going to get all the way through this. It's already 1:15. So if we want to have a Q&A session, we probably want to do that now, right? Okay. Do people have questions? Or should I just continue? Okay, we do have some questions, so let's get that started.
Включен? Скажите, пожалуйста, вот, допустим, у нас есть какая-то инсталляция.
Please tell me, just for instance, there is installation.
I don't speak Russian. Beautiful language, but I have no idea what you just said. I mean, you might have just asked me a American. All right.
Let's imagine the following situation. We have a server, there is an instance of a database, and we actually allocated a lot of memory to this database. Everything is working fine. But how do we know that we didn't give it too much memory? How can we actually, it's like, 78 gigabytes. Is it too much or too less? Probably 16 gigs would be enough. How do we know what amount of memory is enough?
Okay, so there's two responses to this. First response is there is never too much memory. I mean, it's just that simple. I say that in the very beginning. However, I get where you're coming from. What you're asking is, I assume you're running something like VMware, where you're in a shared environment, where you have a finite number of resources over multiple volumes or multiple images. The best way that I could recommend testing is you monitor the underlying OS for the memory that is being utilized. Because what will happen, a really easy way to see this is if you look at, where is it? Let's see. That's really small. Hold on a second. Well, I don't see it here, but if you use free, the Linux free command, for example, it will tell you how much free memory it has. And if you monitor that under your highest production loads, just use Zabbix or Nagios or whatever, Grafana with Prometheus, whatever, it will tell you, you'll be able to see when that drops and where the threshold is of the drop. And that will tell you, I really do have 4 gig, for example, more than I need to have. Now, there is a huge assumption here. The assumption is that you're appropriately configured in the first place, right? Because Postgres is limited in what it will use for a lot of things. And so if you want to know how much is too much, you first have to make sure that you're at least appropriately configured. If you're appropriately configured, then you can watch that free setting, how much free memory is available, and then I would do it over time. Don't do it over a week, but do it over like a month of full production use, because that will take into account growth and everything else, and then you can reduce resource utilization based on that. Anybody else?
And so I would like to ask, if I'm running Postgres on Windows system, and I see that the accused to the disk all the time, how can I reduce it with Postgres tools, not to change the disks?
Well, first, it would be to install Linux and then run it on that. Thank you. But no, where you're going to want to look is things like shared buffers and your checkpoint timeout, because what's likely happening is that those aren't set high enough, and so server processes and checkpoints are happening too often, and it's grinding your disk. So increase your shared buffers, check for queries that may be overrunning work mem. And then also check, for example, checkpoint timeout, and that your BGWriter is appropriately configured. And that way you're not going to get that bursty stuff where it's just grinding all of your disks. But the true answer is just install Linux.
Yeah, thank you very much.
Hi. My question is regarding full page writes, the parameter
Full
you're
page
talking
writes?
about. Yeah, okay. Well, regarding the wall files, right? I'm tending to turn it off because...
Don't do that.
Well, I explain, okay? Because it's greatly increased my performance and the wall size and everything. So I'm always thinking, what's going to happen if I crash my server, and what's going to be my consequences after everything goes bad?
Full page writes is not quite as dangerous as Fsync, right? Fsync is dangerous, period. Full page writes is more of a, there is a chance you will get corruption if you crash, but you may not. Fsync is you will get corruption if you crash. There's no way for me to say it'll be on the 5th crash or it will be on no crashes or whatever. But if you turn it off and you don't have, if you're not running like on a 0 or something like that, there is a definite chance that at some point, if you crash, you might get corruption. Now, here's the catch. Run point-in-time recovery. Make sure you're shipping logs off to another server. So, okay, yeah, you crashed. That sucks. Oh, you got some corruption. That sucks too. No big deal. I am going to restore to the exact point in time. I'm going to recover to the exact point in time to right before the crash, and we're good to go.
Okay.
So that's how I would handle that.
Okay. Another thing, you were talking about Fsync and how not to turn it off. But for me, when I see the setting, it's like a big red button just push on me. Why is it there in the first place?
Well, because back in the day, in the older versions of Postgres, it was a huge performance benefit. Huge. Well, yes, but there's a point where you have to ask yourself, do I want to go fast or do I want to go fast right into the wall? And when I say wall, I'm talking about the brick wall, okay? I would rather take the performance hit that I do. And it's not as bad as it used to be, right? So Fsync itself, if you have a battery back controller or you have with cache, or you're running SSDs, your performance benefit is pretty nominal, if anything. But if you don't have that, you're right. Turning Fsync off is great, but you're guaranteed data corruption if you are running transactions and you crash with it turned off. Why is it there? I asked once, right? I went on the list. I'm like, guys, really, nobody, Grant McAllister. If you guys don't know who Grant McAllister is, he is the guy that architected Amazon RDS and Aurora, right? He is the man. And he likes to come to my talks because I'm smarter than him. Not really. But he does. He actually does like to come to my talks. We get along really well. And I actually brought it up once at PostgresConf in 2015. And I said exactly what you said. I'm like, well, it's such a performance benefit. Why, you probably shouldn't turn it off, but maybe under certain circumstances. And he interrupted my presentation. And he's like, no, leave it on. Okay? So you're right, it is a big red button. And we like to push things. We're like, ooh, I wonder what this is going to do. It's going to hurt. Just leave it alone.
Hello, my name is Vasily Xentil, today company. So my question is about the synchronous and asynchronous replication. The main point is that I have 2 data centers and multi-master state. So I want to know, is there any possible way to be ensured that all the data migrates from one master to another except the synchronous replication? Because asynchronous is not so safe and synchronous is too slow.
kind of answered your own question. So no, I mean the best thing you could. So one, if you have two data centers, you're going to have the network latency issue, right? So there's that problem. The other problem is you're right. Async. The problem with async is you might lose data. Two, the data you won't necessarily lose it, but it'll be inconsistent and therefore cause conflict. Those types of things. My honest recommendation: don't run multi-master. Okay, usually, now, you might be the exception. There's 230 people in this room. You might be the one exception. Usually people that run multi-master do not understand the problem. Okay, I'm not saying that to be rude. It's just the truth. I often hear people, I want to run multi-master because it's that big red button, and it's a sexy red button. Multi-master, the idea that no matter where I insert my data, it just magically works. There's a reason Oracle Rack cost $1 million, right? There are some weird solutions you can do if you want. For example, in the newer versions, you can use logical replication to merge result sets. So it's not actually multi-master. It's you write to this one and you write to this one, and then they replicate to each other, which is not really multi-master. It's kind of a different thing. And so you could look into that. But the problem with sync is if you do synchronous, especially synchronous multi-master over a WAN, basically over a network interconnect that's not local, you're going to kill your performance. There's no way around that. We just haven't reached that level yet. Now, that being said, look into like Yugabyte. Okay? Yugabyte is a company. They're in the Bay. I'm sorry, in California. It's open source. What they did, they're actually the founders. Who here knows what Cassandra is? Okay, we all know what Cassandra is? Okay, Cassandra is kind of a MongoDB competitor. Well, these guys said, well, I've kind of reached the limit of Cassandra. So instead, they built it on top of Postgres. And they have geographically distributed, replicated nodes where you just point and it figures it out. So I would look at Yugabyte. That's an option. Another option, which is similar, but it's going to feel weird, is Cockroach. So Cockroach, what they did is they said, we don't want to deal with having to have all new drivers, all new syntax, that type of stuff. So they put a layer of Postgres on top of a different database. And it's also geographically distributed, and it's also open source. You're welcome. Well, there's one more. The other one is ProtoDB. Now, this is interesting because it's actually an app layer over data sources, and it's what Facebook uses. Okay, so those would be three. You're not going to get it with Postgres proper, but something similar, you should be able to pull it off. You're welcome. Anybody else? Cool. Thank you for your time.